We are going to talk about the microservices pattern and Akka, basically. I'm Fran Perez. I'm a senior software engineer at 47 Degrees. I'm going to be, well, I'm husband. I'm going to be father of twins very soon. And there are my contact details if you want to stay in touch or ask whatever you want. OK, first, how many of you has experience with the microservices pattern and especially with Akka? OK, cool. OK, maybe we need to have some knowledge, not a very deep knowledge on Akka, and especially on the actor pattern. But I think we can follow perfectly the talk. If you want to ask anything at any time, don't hesitate to interrupt me and ask whatever you want. So this is the roadmap we are going to follow. We are going to talk about scalability. Especially, we are going to describe the scalability cube that is named or described in the Art of Scalability book. And based on that, we are going to propose a project. That project is the base where we are going to explain different, the microservices pattern, how we can use Akka to implement this dummy project. You are going to see how this project can be decomposed functionally, what is event sourcing and CQRS, and well, some concepts like the data partitioning, horizontal duplication. And finally, we are going to see some code snippets on how we can do that with Akka. At the end, we are going to see a very, very short demo. And finally, we are going to see a few common errors or problems we have when we are implementing this pattern with Akka. So let's start. Scalability. This cube or this diagram comes from the Art of Scalability book. It's a very good one. I recommend you very hard to read it. And well, we can scale in 3 different ways. The first one could be if we have a very big application, we need to identify the different functionalities we have in our project or in our main one. And this is the y-axis. Then we have the x-axis, which is just cloning. It doesn't have to be just data. We can be cloning data, but we can be cloning applications as well. The same application can be deployed in different nodes, and we can have a load balancer in front of them, redirecting to one or another. OK, so finally, the data partitioning, which means that if we have a set, imagine we have a set of attendees or customers or whatever, and we don't want to have all the customers be managed by the same node or the same node. So we are going to be able to split customers or entities into different nodes. So every time a new message arrives to our system, it's going to be handled by exactly the same node. Yeah, there are some details that can be made that the node, if we have an outage and we need to bring up the cluster again, maybe the messages, depending on how we are implementing it, can be handled by the same node as before or by a different one. But in essential, we are all those messages are going to be handled by the same node. So let's introduce a dummy project. Let's say that we want to build a conference management system. And this is our main goal. Where we are going to be focused, and this is the example we are going to be working during all the talk. First thing, when we are talking about our application, and we want to apply the microservices pattern, which we are going to be just after this slide, we need to decompose the functionality of our application. OK. We need to decompose, or we need to extract to know all the functionalities that our application is going to have. That is sometimes hard because we don't have or we don't know feature specifications. So sometimes we can discover new functionalities or new microservices after the application has been built or deployed to production. So in this matter is where the microservices pattern comes. And first thing we need to take into account is that the consistency level we are going to have implementing this pattern. If we need transactional consistency, this is not maybe the best approach for you, but almost everything in our lives don't have transactional consistency. Instead of that, we usually have eventual consistency. Do you know what that means, eventual consistency? Yeah? OK. So after that, we need to identify the domains. We need to identify all the functionality we want to include into, or that makes sense to have in a single microservices. We need to identify the domains, the different areas we have in our whole application, and each of those areas are going to be a different microservice. It's not easy, and at the same time, that approach made us make it possible to have a very isolated context. So it's very easy to deploy each of those microservices. Sorry. OK. Yeah, OK. So once we have identified our domains, and we know what are our bounded domains, and we have an isolated context for each of them, we need to identify relationships. Relationships are the most difficult part in the microservices pattern, especially because we are not solving everything with this approach. So the complexity of a system is still there, but we are just moving the complexity from one point to a different one. And the problem with this relationship identifying is that we need to be ready to discover new relationships between the microservices we build, because sometimes they are hidden, or a new feature can make that a new relationship arise. And finally, I want to make like a distinction. Functional decomposition is not the same like code decomposition. We are going to decompose the functionalities of our application, but that doesn't mean that we can't have like a framework, like a custom framework that is going to be shared by all the microservices. So we could have potentially a library that contains all the, a common library that contains all the different pieces of code that makes our framework at the end. OK? Any questions so far? So focusing on our conference management system, we can have, for instance, a code for paper management feature, an attendees management, segmentation, for instance, email management, or analytics. They are just examples. For this talk, we are going to be focused on the attendees management, and we are going to use the 4 kings: Scala, Akka, Kafka, and Cassandra. This is the architecture. We are going to be focused now on a specific microservice, which is the one about the attendees management. So this is the architecture we are going to build. We are going to be based on Kafka, like the input and the output for the write operations. But at the same time, we are going to have a read side, which is, we are going to see that in more detail very soon, about the CQRS. But mainly, we want to have like a write API based on Kafka. But additionally, we want to have a read API based on HTTP. At the same time, I wanted to like decouple to show better that we don't have to be we don't need to have the same technologies in both sides. So for the write API, I chose to have a CSV strings, but for the output, the read side, I chose like the JSON representation. Potentially, the microservices that is like shadowing is because the output from Kafka can be potentially consumed by a different microservice. To build all this stuff, we are going to base the implementation on the Akka ecosystem. We could have chosen different tools, but for this purpose, we chose Akka streams, Akka classifying tools, especially the sharding region, Akka persistence, and well, Akka persistence query and Akka HTTP for the for the read side. Let's start with the event sourcing. As we said at the beginning, we are gonna base the entity in event sourcing. That means that when we receive a new message, that message is gonna modify the state of that entity. And if we want, we are not gonna, if we want to retrieve the state or have the state of an actor, of an entity, we need to reply all the events that came and modify the state to have exactly the same state that we had before. Then we have the CQRS, the Common Query Responsibility Segregation. As we said, we are going to use Kafka on one side with a CSV representation, and on the other hand, we are going to have HTTP endpoints, exactly only one, but HTTP endpoints with a JSON representation. Data partitioning, as we mentioned previously, we want to have, if we have a set of data, we have a set of entities. When a new message for a specific entity arrives, we want to have the same node to be responsible for that entity at any time, at every time. So we are going to see the code later. I think it's going to be easier for you to get the idea. But basically, we are going to have an ID. We are going to get the hash code for that ID. And then we are going to get the module of that hash to know which node is the one that is going to handle that entity. Since the ID is always the same, the hash code is going to be always the same, and it's going to be handled always by the same node. And finally, talking about horizontal duplication, we are going to see we are based on Cassandra, so the data is going to be replicated. For instance, if we have a Cassandra cluster of 5 nodes, our data could be replicated in 3 nodes. That is the same data is going to be present in 3 of the 5 different nodes we have. At the same time, as I said previously, horizontal duplication is not only about data, it is about applications as well. And we are going to see that the HTTP application that is going to be running is returning exactly the same and can be after or behind a load balancer, so they can be redirected to the right one, or depending on the balancing strategy you chose, round robin or whatever. So let's see now some code. We are going to model our application with this structure. We are splitting the application in 2 different SBT modules. We have on one hand, we have a model module containing all the public API we want to expose for services, microservices integration, for instance. And additionally, we have a different module for the application. That allows us to have different or isolated dependencies. So for the application module, we have all the stuff we need to have, but we don't need anything about the representation. So all the things we want, or all the libraries that we need for the API are in a different context or module. Let's talk now about the CQ, or the Common Query Responsibility Segregation. I'm going to go through the different, we usually talk about CQRS both at the same time, read and write, but I'm going to go first on the right side. Let's do all the things we want to do for write operations, and at the end, after this description, we are going to see how we are implementing the write side. So for the Kafka API, or the write API, we are using this API. We are exposing a command and an event. An event is just the representation of the response or the side effect that has been produced by that command. We have an ADT, to be able to handle different types of commands. At this moment, we only have one, but imagine we have more than one. And with this code, we are consuming events from or messages from Kafka. We are parsing them because we are reading CSV strings. And we are sending those, as you can see in the, well, there are not line numbers, but in the first case, in the pattern matching, we can see that we are sending an entity envelope to an actor. That actor is a sharding region. We are going to see the sharding region in a couple of minutes. And additionally, we are going to implement a producer. That producer is going to be able to send new messages to Kafka. But at the same time, we don't want to use this directly. So we are going to implement a helper, an actor, which is the one in charge of publishing new messages to Kafka, which is this one. Okay, it's a very simple one. We are just receiving a message, extracting some information from it, and creating a new response, publishing it into Kafka. So when we are talking about data partitioning, and here is where the sharding region comes, we have an incoming message, as we saw in the consumer, and we are sending an entity envelope to the sharding region. This entity envelope contains an ID and the proper command. So based on that ID, we are gonna, as I said, briefly explained before, we are getting the ID, we are getting the hash code for that ID, and we are producing or getting the hash code and the modulo for depending, the modulo between of that hash code and the number of nodes we currently have. That number of shards could be a different one than the number of nodes we have, but we are taking them from the seed nodes length that we have configured in our configuration. Event sourcing. Let's see the implementation. As we said, well, let's see something here, because in the sharding region, we are not only defining how we are going to shard our entities, but at the same time, we are describing or pointing which is the entity actor we are going to use to handle those entities, those messages. This is in the second row on the cluster sharding start. So that entity actor is basically a persistent actor and an actor logging just to provide logging stuff. Persistent actor means that we are going to be able to take that message and store it into Cassandra. So that is a new concept that comes now, which is the passivation. Do you know what is the passivation of an actor? Yeah? Okay, well, basically, when we have an actor, it is in memory. So imagine we have 10,000 or 10 million customers. It's not something that we want to have 10,000 million of customers or actors instantiated or having them in memory. So we can configure the application to kill those actors that for a specific amount of time hasn't been receiving any message and doesn't do any kind of action. So since we can kill and remove that actor from memory, we need to be able to reinstantiate the same actor and go to the same and have the same state it has before it was passivated. To do that, we are going to use Cassandra. But at the same time, we need to decouple or have a specific function that is going to apply that change to the state. But that change is going to be applied in two different ways, in two different points. The first one is when a new message is coming, because we are modifying, editing the state. But at the same time, since we are recovering, we are reading those messages from Cassandra, we need to replay them again during the recovery stage. This is the body. We are going to add some more things at the end, but at the moment, we only need to see or to know that we have a receiver where we are going to be handling those incoming commands. First of all, what we are doing is translating that command into an event, because the event is the actual one which is going to modify our state. So No worries. So why are we doing that modification or that translation before persisting? Because once we have it persisted, that event that has been persisted is the one that is going to be applied when we are recovering it. So we want to have exactly the same. We want to use exactly the same data object when it is a new one or when it is an old one that it has been replaying. Okay? Any questions so far? Okay, cool. What's the time? Okay. So here, this is the special receiver that is going to handle the recovery stage. So once an actor has been passivated and a new message arrives for that entity, we are going to recover, we are going to replay all those events that came before to get exactly the same state. And that is done with this receiver recover. We are overriding it because all those methods we are seeing comes or are implemented in the persistent actor trait we saw at the beginning when we saw the definition of our actor. But at the same time, we don't want the default behavior. We want to make special things on that. Our business logic is different in each project, so we need to override the behavior of that method. Let's see now the horizontal duplication. We are going to see it's very, very simple. It's Cassandra. We are going to use the Cassandra Persistence, the Akka Cassandra Persistence API. In the body of the actor, we are seeing that we have a persist event. That persist event is the method call that is going to actually persist the event into Cassandra. For our purposes, we don't want to, but at the same, since as I mentioned, when we are recovering from a passivation, we are replaying all the events. But imagine we received 1 million events. We don't want to replay all of them because it's very it has a high cost. So we want to have like a snapshot, not like we want to have a snapshot. So we are like storing or saving a specific state at that moment. So when we are replaying the events we have in Cassandra, we don't have to replay all of them. We are going to take the latest snapshot we have, and then based on that snapshot, we are going to apply all the rest of the messages that weren't included in that snapshot. Not sure if I explained it very well. Okay, so as I mentioned, we are overriding those default behaviors, and for the persistence, we are doing that. We are persisting all the incoming events, but we are not taking snapshots every time a single event arrives. We are taking snapshots based on a custom business logic. In this occasion, we are persisting every 5 events, we are taking a snapshot. At the same time, taking a snapshot is something that increase the size of your data into Cassandra a lot. So we need to take that into account, and that it doesn't make sense depending on the business logic as well, obviously. But we don't need, in the most of the situations, to have all the history of all the snapshots we have been taking. So we can implement a way to remove all snapshots that we don't care about them. To do that, we need to manage the different snapshot messages. So once we created a good snapshot, a message is sent to the same entity actor to let him know that the snapshot has been taken. So once we know that the snapshot has been taken, we can remove the ones we don't want. So yeah.
Why don't you have one single snapshot?
You can. You can have just.
A queue pattern.
Sorry?
You have a queue pattern.
Yeah, you can have just the latest one, but depending, I just wanted to show that you don't need to have only the last one. Depending on your business logic, you can have one or more, because imagine you are using those snapshots for some other stuff or whatever. So you can keep just the latest one, but if you don't need that, you can have as much as you want, as many as you want. And now, finally, we are going to see the other CQRS side. where we are reading data from the Cassandra entity where we have been storing our events. It's very simple. We are exposing a very simple API, a single endpoint. It's a GET operation. We have the entity ID or the entity name, the attendee name in the path of the endpoint. We are going to call a service to get the attended conferences for a specific entity. And to be able to do that, we are going to use the persistence. We are using the persistence query, the Akka persistence query library, which provides you to query data from the journal or even from the snapshots. Well, sorry. So finally, the structure of application we just built is this one. We have two different modules, the application module on one hand and the model module in the other hand. So we can have different jar files and have the model, jar file like a dependency for a different microservice which is going to be consuming or interacting with that microservice. At the same time, we included in the model module, we included all the representation stuff, like the CSV serialization and the serialization, the JSON one, because we want to provide at the same time to avoid code duplication between microservices. We want to expose a way to serialize and deserialize those messages that are owned by a specific microservice. Let's see a demo. Whoa. Whoa. I can see my mouse. So I have here 3 nodes of the same application. Those debug messages are just the gossiping. Yeah.
What if you change the number of shadows in the cluster?
They are going to be, imagine you have.
Like you can change it on the fly, like you can scale on
It's
the fly?
In this occasion, we are taking the shard number based on the length of or the number of nodes we have in our cluster. That is writing in the configuration. If we want to modify that, we need to modify the configuration, and we need to rerun the application. We need to restart the application to read the configuration. You can have some GMX command, like you can inject on the fly to the application. If you want to change configuration values on the fly, you can use some services like Console or something like that, but not. And if you have 3 nodes and you have a shard number of 4, what happens is if you have 10 elements, you have 3 nodes, you are going to send a message to a different node based on, imagine the first one, modulo 3, it's 1. So it's going to be to the node 1. If you have the ID of the second message 2, modulo 3, it's going to second node.
My question was actually concerning Akka clustering, because shards are based also on Akka clustering. And I thought that, for example, we have a number of clusters, a number of nodes, like 3, for example. And then if I add a single node, then the shard it's going to be our.
No, but you can handle the elasticity, but you need, because you are adding a new node to the cluster, and you need to manage that stuff. That can be made with a different library coming from the Lightbend stuff provides you some tools to dynamically modify the size of your cluster, and the information in those nodes is going to be rebalanced. Okay. So those are some tests I made before. Okay. So imagine we have a, well, let's Candela is the name of one of my future daughters. Let's use the other. Okay. So imagine Emma only attended one conference at this moment. We are going to send a command through Kafka. It's difficult to see the pointer here. You are going to say that Emma is attending Scala I/O, okay? And this message should be handled sorry. So we saw here that this message has been handled by the second node. Okay. Now here. Here, you can see that this message has been handled by a specific node. If now we send a different name, like Fran, Seville, this one has been handled by node 1. So depending on the entity ID, the information, the message is going to be handled by one node or the other. If we send a new message for the same entity ID, in this case, Emma lambda word, you're going to see that the message has been handled by the same node, which is here. Yeah, this one is the passivation. And here we have that the lambda word message has been handled by the same node that the first one. And at the same time, we are seeing that once a command has been handled, an output on Kafka is being produced as well. So here in the right side, we are seeing that we are getting a new CSV saying that Emma attended lambda word here in that side. Additionally, the read side, we are going to see that we have 3 different nodes, and now we have that Emma attended to Chiclana, Scala.io, and Lambda Word. But this is a response from a specific node. We can check that depending on the node, we are going to get exactly the same application, because the thing that a specific message has been handled by a specific node doesn't mean that all the read applications or the read side on the different nodes are going to return different information. All the nodes in the read side are going to return exactly the same information. And here we can see that Emma in the other node is returning exactly the same, and in the third one is returning exactly the same. The 3 conferences she attended, or futurely attended. And well, finally, let's see. Some common problems, like the relationships. At the beginning, we said that sometimes we have hidden relationships, or a new feature comes from business and we need to implement something new. And we need to be ready, as we mentioned, to understand that we can have new relationships and that can increase the complexity of our system. At the same time, the split brain, the serialization, that's the split brain issue, which is that if we have a cluster, imagine 3 nodes, as we have been talking about, and there is a network issue, and one of the nodes is not seeing the other 2. But it is working. So since we have in our configuration set that the minimum number of nodes we want, imagine we want to keep the cluster alive, we want to have just 1 node, or imagine we have a cluster of 5, we can have 3 or 2. We can, at the end, we can have like 2 different applications running on production on the infrastructure, reading from Kafka, but with the same group ID. So if we are reading with the same group ID, some of the messages are going to be handled by one cluster, part of the cluster, and some of them are going to be read by by the other nodes. But the ones that have been read by one side are not going to be shown or visible by the other side. So we have a problem where the same application is processing messages in two different ways. That's why we are talking about splitting the brain. Additionally, serialization. Serialization is a problem. It's a problem because when we have a cluster, everything is traveling through the wire. So everything is serialized. And we need to take into account as well that we are persisting events. So if we are persisting events and we modify the shape of those events, we need to deserialize those events again to be able to create, to instantiate the object and apply that to the state. So if we made a modification, we are going to have an exception thrown because the string that is stored doesn't match with the object that we currently have. To solve that issue, we have different possibilities. We have, on one hand, we have the event adapters feature that comes from Akka, but at the same time, we can use specific or different serializers like protobuffer or Avro that allows us to have versioning. A different issue we can have related to messages and traveling through the wire is that the message size matters in Akka. There is a configuration value set in Akka. We can modify it, but it's not a very good idea because if we increase it, we are saying that we want very big messages traveling through the wire, and this could be lead you to performance issues. So this is another possible problem we could have with this pattern, but we can, or batching messages or splitting big messages into different small messages to solve this issue. One more problem we could have is the persistency weight. This is something we talked briefly previously about the snapshot size we could have. So it's a good idea to, or just keep the latest snapshot as a sorry, I don't know your name, mentioned, or remove the ones we don't care about. And finally, since we are talking about a distributed architecture, logs are not only in a single location. Logs are in different locations. So we need to aggregate or have a tool to aggregate those of them, or to be able to debug properly an issue when we are talking about production problems. That's all. Question? No. Here. Yeah, there is a plugin, a library. In this occasion, I'm using the ones that are provided with Akka Persistence Cassandra. I'm not using Akka Persistence Query, but it's exactly the same. There is some methods that allows you to query the journal table from Cassandra. So the state, at this moment, the state only contains the amount of conferences attended, but not the list of conferences it attended.
What I didn't understand is, and I really wanted to know is, the query side when you run the server, the HTTP, is coupled with, is member of the cluster, or
no, they are completely separated. We could exactly, we could even have a different application running and deploy it in a different way, but everything is in the same application at the moment in this example. Yeah.
Possible to view the CSV data that is coming into Kafka and the events, and get rid of the Cassandra source of events.
Sorry, I'm gonna. Sorry, I didn't.
Is it possible to view the CSV data data that's on Kafka as the events and get rid of the mapping from the commands in this case in Kafka to the events in Cassandra?
It can be done, but I don't recommend. Well, the question is, can we modify the state using directly the incoming data in CSV, the format, instead of translating it from a command to an event? It can be done, but it's not a normal practice because we usually include some metadata information into the incoming message. So we don't want to store the whole information into Cassandra because it's going to increase the size a lot. So we are like removing everything. We are taking only the information that is going to really affect the state of that entity. So at the same time, we want to decouple the input than the output, because the event at the end is what we are sending to the Kafka output channel. Yeah or no? Yeah, well, the same.
In your demo, if you keep the one node and you send the message schema, what happens?
Sorry, can you
If you keep one sharding node, supposed to be the second node, and you're sending a message with the EMA, what happens?
Well, all the messages are going to be, all the actors, the entities are going to be, the question is, what happens if we kill one of the running nodes and we send a new message for Emma? Okay, the information that we have in the nodes are going to be rebalanced between them, and this new message for Emma is going to be handled by a different node. Let's see it. So, for instance, Emma was handled by the second node, which is this one. Okay, I'm going to kill it. As you can see, the other consoles are starting to do things. So they are rebalancing and doing stuff. And now, if we send a new message for Emma and saying Leon, it's handled by another node, not the one that is down now. Okay. There was a different.
Actually, two questions.
Yeah, sure.
Am I correct? That's major parts of what you
Sorry, I'm gonna.
major parts of what you showed here written
Yeah. We can write. This example is a very simple one. And we, sorry. Maybe it's not the best for you to be moving. Sorry. So yeah, as you mentioned, we can implement this functionality very easy with a different framework. I wanted to show a very simple one and how we can build this with this architecture with Akka. But yeah.
Okay, and second thing regarding the parts where you mentioned deactivation of the actors. So, okay, deactivation is cool, but for example, if we have traffic spikes, is there something out of the box that would let us automatically scale our cluster?
Well,
Spark, for example,
you can use a cluster management tool to scale up and down the size of your cluster.
yeah,
But
is
based
there
on
something out of the box, so I don't have to manually do development?
no, there are things. I don't have anyone on the top of my mind at this moment, but we have used a couple of tools that provide you that functionality. But it's possible to do that.
Question.
Yeah, sure. Sorry.
You know, when you are reading this HTTP service, it reads information from Cassandra. Is this right?
Yeah.
But at the same time, it happens that this act is probably alive and holds up-to-date information in some node. So hitting is this also right? This
Well,
act,
it's-
if the actor is recent and hasn't been pacified, it must be alive in some of the Akka nodes.
The thing is that we have eventual consistency. So if we produce a write operation and we are reading, if the write operation hasn't been handled on time before the read operation has been queried or made, the information we are going to have is not yet into Cassandra. So it's consistency level. It's, we don't have, if we want to have that behavior, we should go for a different approach where we can have.
I'm fine with this. My question is it really necessary to hit the Cassandra for a read operation because you have this information in memory on some of the
No,
machines?
I don't have that information in memory. Let me show, because the state of the actor is just the amount of conferences that a specific entity went, but not the whole list, because the whole list could increase very, very high. So imagine an attendee attended to 10,000 conferences during his life. So we don't want to have a list of 10,000 elements in memory. That's why we are using different sites or approaches.
Okay, thank you.
Welcome. Yeah.
Just maybe to, because you asked for if there was something out of the box. Actually, Akka offers that. You can use, for example, some level metrics and so use some actors to demand some resources and spawn some new nodes actually. If you read the documentation, they do something like that. And actually you can use like beans, commas that relate to the JVM of the nodes because they share some membership and they're all aware about everything because there's no master, Every single member of the cluster can see every single member, so they can agree upon that because actually with shards, they're based on the Akka clustering feature and you can actually expand some new nodes actually. Lightweight promotes the elasticity, not just the scalability. So you're gonna be able with Akka to expand some new nodes on the fly. You should be careful just with what is the criteria to actually to spawn some new nodes.
But then it means that the code has to be aware of the scaling features, right? So it's not something that hovers on top of the app and automatically.
You can do it both. For example, with Kubernetes, something like that, you can do it in the container side. So application doesn't need to know everything about it, but you can also have some intelligence in the application level.
The Lightweight subscription library, for instance, provides you a way, a utility, for doing that.
Source, you need to wire
When Lightweight provides a subscription, so using the subscription library, you can. But I didn't want to talk about privacy, or that's all. Something else? More questions? Okay, so that's all.